So packing is opposite of fragmentation, right? When do we use packing? Anybody? When can we use packing? Yeah, when your packets or your SDUs are very, very small, right? And then you need to put more than one, then use packing. Now there are two kinds of situations. One situation is, so basically when you do packing, then with every SDU you put a 2-byte header in front of it, which basically tells the length of that SDU and tells you that this is a packing header. So, but if all the SDUs are the same size, which happens in the case of ATM cells are all same kind and they're very small. So if you're packing ATM cells, then you don't need to put those 2 bytes, and you just put that in the header itself that these are fixed size SDUs. Otherwise, you put this header, which is the packing header, packing subheader. Grant management subheader is used for requesting the bytes. So when you are requesting some transmission opportunities, you have 2 ways. One is that you can just send them a whole packet request which says that I want 300 bytes or whatever. But also you can put this header in any PDU which is already going. And if you put this header, then the header basically has these 3 parts in the case of UGS and this case of non-UGS. In case of UGS, these are the 3 parts. In case of non-UGS, it is basically the number of bytes that you need. So that is all you need to tell. In case of UGS, which is a fixed rate, remember UGS was CBR, constant bit rate, in that case you put this which says now poll me. That means I want to change my rate. Okay, and this first bit is a slip indicator, which is basically when you are getting something at a constant rate and some things are going out exactly at the same rate, you should not have any queue build up, right? But when your queue start building up, they say you are slipping, right? Because you are not able to send out as fast as you are getting something in. So that slip indicator is simply saying that the queue has built up. So I want to change my rate. So please poll me. So the number of incremental bytes. So that is this header, right? And then there is an extended request, which is used for ERTPS class. So there are 3 classes. So we saw one for the UGS, we saw for the non-UGS, and then the third one is for ERTPS. Anybody remembers what is ERTPS? Go ahead, yeah. Yeah, enhanced real time, but what is it? Is it CBR or BBR, variable bit rates, constant bit rate? Huh? Anybody else remembers anything about this? Huh? Yeah, it's on-off CBR. You got to come 15 minutes earlier every day. Every day. Just make it a plan. Right, so it's on-off. So basically, this one has 11 bits for incremental request. And then MSB is set, then this has 3 parts actually, as we said. If the MSB is set, then the 4 bits indicate that you request me, the polling size, and then if the queue is built up, then you set up the MSB bit, and then the base station will shift. So it's somewhat similar to this slip indicator stuff, but combination of these 2. So your first bit is actually slip indicator, which is you set the MSB and then the it will get the grants to you earlier so that you can clear up your queue. And then these are used for how much more bytes I need. Right now 11 bits, and then this one basically indicates that if MSB is set up, then basically the 4 bits indicate the requested polling size, which normally should mean that please poll me, but I don't know why they need 4 bits. So 4 bits means that they might indicate that increase my size by some amount. Although polling means that you ask me, and then when you ask me that time, I tell you that I need so many bits, so many bytes to be sent. So that is those are the headers, and then how the fragmentation packing is done is here. Fragmentation is basically breaking a SDU into multiple PDUs. So you take, let's see, this is an example right here. You take this SDU, and part of it goes into this PDU, and the other part goes into this PDU. So that is fragmentation. Packing is putting more than one into one. So here we have packing because we have some part of this first SDU as well as this SDU, more than one SDU. And concatenation is when we combine many PDUs into one file layer request, basically. So multi PDUs in a burst. So this is what we call in the file layer, we call it as a burst. And if you remember the burst in the 2-dimensional diagram, we had burst 1, burst 2, burst 3, burst 4. That is what BS has allocated, and that may or may not include complete PDUs. So that's what happens is that you may have PDUs, and some of them may fit and some of them may not fit. So whatever fits there goes in, and the rest is put in the next burst. All right, so there are 3 words here. Key is to recognize these 3 words: fragmentation, packing, and concatenation. All right, we've already talked about fragmentation and packing before, so it should be clear by now. But concatenation is a new word, which is basically combining many PDUs into a burst. Okay? So what is feedback? Basically, feedback is the channel quality. So the receiver knows what is the quality of the channel, and it has to send the transmitter that these bits you sent before were so much in errors, or they were, what was the error rate. So when a base station wants to get a feedback from a SS subscriber station with advanced antenna system, then what it does is it sends this header, and this header basically is 1 byte long, which says allocation offset and the feedback type. So allocation offset tells what is the number of slots after which the SS should send the feedback, and then feedback type is downlink measurement, MIMO feedback, antenna number 0 MIMO feedback, antenna number 1 MIMO feedback, and so on. Okay, so there are many different kinds of feedback that could be there. So they have 2 bits, so basically 4 feedback types, and then it says that you should put that feedback at this location in your uplink burst, right? And so that is the location in the uplink burst. This is request is going down in the downlink, and when you send back in the next uplink opportunity, that is where you should put it. So I will find it exactly at that place. and there is a ARQ feedback. And ARQ feedback is basically acknowledgement, which tells which packets, which blocks were received, which blocks were not received. Now there are two ways to tell the blocks received or not received. One is that we could say I have received everything up to block number 35. So that is a cumulative ACK, right? Second way is that I have received up to everything up to 33, and then I have received 35, but I have not received 34. That would be what we call selective ACK, right? And so those are two kinds. So you put the ACK type here, 2 bits. 00 means selective, where we will send you the starting block sequence number and the bit map. So this bit map indicates the blocks that have been received or not received. So if I say starting number 33, then 33 will have a bit, 34 will have a bit, 35 will have a bit, 36 will have a bit, 37 will have a bit, and if the bit is on means the packet was received, block was received. If the bit is off means block was not received. So you know exactly which blocks to send. All right. So everybody understand the meaning of bitmap, right? Clear? Bitmap simply indicates which blocks were received, but we just basically we give block number, first block number, so you know exactly which block we mean, right? So that is selective. Cumulative, in this case there is no bitmap required. You just say everything that up to 35 was received, right? Then you could have cumulative with selective, where selective up to a BSN and then a bitmap, and then 1 is cumulative with a basically 1 bit status for the n blocks. So basically it says that cumulative with block sequence number, when this is 1, in that case it might say that okay, I got everything or I did not get everything. So 1 bit indicates whether this is we got every block, 1 bit is used for acknowledging everything or not acknowledging everything. So 0 or 1 bit map for all n blocks. So there are 4 different kinds of acknowledgements, right? And 4 different, so the CID is the connection ID, and last means this is the end of feedback and element, otherwise you might have a bunch of these. And then acknowledgement type, block sequence number, which goes in these fields, BSN. Then you have the ACK map, which is the bit and this is basically how many bits in the map. So number of ACK maps, and there are shown 3 are shown here. Each of them are 16 bits. So you have 48 bits here as shown, but you could just have 1. In that case, it would be 16 bit, right? So going back again, let's see. We have 1 plus 2 3 plus 11 is 14 plus 2 16 bits. So total is 16 bit of CID, 16 bits of these headers, and then each map is 16 bit. All right. The key point is that most protocols where you have this acknowledgement business, you have to decide whether you want to have selective acknowledgement or whether you want to have cumulative acknowledgement. TCP generally has had what kind of acknowledgement in TCP? Anybody remembers what kind of acknowledgement in TCP we use? Anybody remembers TCP? Some 473. Well, so normally TCP uses only a cumulative acknowledgement. All right. There is an option for selective acknowledgement which was added later for high-speed networks, and so there is an option, but I don't know how often people implement it and use it. So it may be implemented and not be implemented, depends upon the implementation. Here the standard allows all kinds of combinations. So this is what shows basically in IEEE if one says, well, I want selective, one says I want cumulative, they say, okay, we will put both and all possible combinations of those. All right, now scheduling. So scheduling has to do with which packet goes next, and there are two schedulers. One is in the base station and one is in the subscriber station. At the base station, it allocates both the uplink and the downlink, right? So it decides, depending upon its own queue, the base station keeps the queue of the packets going to different stations, and then it decides which queue, how many packets to take, and how big burst to give to that station, right? So that is downlink. Then it also knows how much each station needs to transmit, how much is the queue at each station, so it decides how much to give to each station. So that is the uplink scheduling. So this is done, and the station is told that you have 480 bytes to be sent in the next frame. Then the station decides, the station scheduler decides among its queues as to which 480 bytes will go up. All right, so we need two schedulers, and the base station scheduler does both sides, okay? But the subscriber station scheduler only decides which of the packets in its queue goes into the total allocated by the base station. The total is allocated by the base station, but which individual packet goes is decided by the subscriber station. Is that clear? What is the job of the subscriber station scheduler? No? So let me ask you again, what is the job of the base station scheduler for the uplink traffic? What does it do? Anybody? Not clear to anybody. How does the uplink bandwidth get allocated? Huh? Yeah, by the base station scheduler. So let's continue along that line. So base station scheduler decides that we have 11 or 10 stations here, they want to transmit, how much each can transmit, right? Then if I decided that the base station decided that, okay, this station is going to get 480 bytes. So what happens then with those 480 bytes? What goes into those 480 bytes? Who decides that? Yeah, that's what the subscriber station scheduler. We need a scheduler in subscriber station because there are so many packets with so many priorities and so many queues that we need to decide which 480 bytes go up. Right, so that's why we need two schedulers. The base station scheduler decides the total, and then the subscriber station decides which particular packets go up in that total. Now it's clear? Okay. Let's see, link adaptation. So one of the things that the scheduler has to do also is what we call link adaptation. Is that it adapts the amount of the size of the burst as well as the coding used in that burst depending upon the station. Some stations which are far away, they will get a coding which gives them how many bits per hertz, lower or higher bits per hertz. Stations which are far away, they get lower bits per hertz, whereas the stations which are closer get higher bits per hertz coding, right? At the same time, they also need to decide how many total slots to give to each station. Some stations are close by and some stations are far away. So we have to decide now, given that we have decided their coding first, so we know, but then you have to decide how many hertz to give them, right? Which is basically how many slots to give them. And that is also done depending upon the class of the traffic. If it is a time critical traffic, if they have a guaranteed throughput, then you have to decide that, now we have to give them so many slots. So that is called adaptive, that is called link adaptation. Link adaptation means we change we decide the parameters for each station's link, right? And link is basically the connection between the base station and the subscriber station. So the link starts. So base determines the content of the DL and the UL portion of each frame, and it determines the appropriate burst profile. It decides what is the code rate, what is the modulation level for each subscriber. It also determines the bandwidth requirement for each individual subscriber and based upon the service classes and so on and so forth. Okay? Any question on this? Okay, good. That brings us to the end of WiMAX lecture. So some things to remember here are, in the MAC part is that everything is centralized in the base station. This is different from, well, how is it different from Wi-Fi? The resource allocation. In resource allocation in Wi-Fi, how was it done? Anybody remembers that? What do you have to do if you have to send a packet? Right, so you send RTS, CTS, right? Now, is there advantage or disadvantage to RTS, CTS? See, what happens is, that was contention based actually in some sense, right? A lot of bandwidth is lost because people have to just draw a random number and then wait, right? Here there is no random drawing, every single bit is used. All right? So because we are talking about here high-speed network, every millisecond has so many bits. That's why they don't want to use the old Wi-Fi kind of stuff, and it is better to just be centralized and do it that way. I mean, we do have RTS, CTS kind of thing, but it's not called RTS, CTS. What we have here is request and grant. So request is similar to RTS, where you say, well, I want to send 400 bytes. And the station says, okay, you can send 200 bytes in the next frame, right? And then it says you can send another 200 in the next frame after that. So that is in place of RTS, CTS. What we have is request and grant, but there is no waiting. Waiting means unnecessary waiting. Obviously, you have to wait for your turn, but there is no idle time. Centralized scheduling. Second thing is, they want to use every single bit, so there is fragmentation and packing. If there is a space in the PDU, we take the next SDU and put that in, right? And there is a fragmentation and packing, right? Both of them. And then we have ARQ and HARQ. ARQ was the retransmission, right? We divide the packets into blocks, and if some block is not received, we saw the acknowledgement. If the acknowledgement is not received, we retransmit it. What is HARQ? Anybody remembers hybrid ARQ? Yeah. Good. Excellent. So that is the key thing. Hybrid is that it is both MAC and PHY combined. That's why it is called hybrid, because we need the help of the PHY layer. The PHY layer codes it differently, right? And then it sends it to the other side. Whereas in the ARQ we send the same packet, same coding, everything is same. It's just retransmission. ARQ is retransmission, whereas HARQ is retransmission with a different coding. Then complex scheduling to provide guarantees under variable conditions. What we have not gotten into is how do you schedule all these 5 classes of service we saw, right? And so that is a whole topic of research and papers and so on and so forth from our group. Actually, quite a bit of work has been done in that area.